Swayam Prabha. Digital India. Educated India.
Hello all, welcome to Astrochemistry. This is lecture 40. It's also doubling up as tutorial 10. So in the last tutorial, we had started with a rather lengthy problem. Well, we started off with the expression, the Planck's expression for rho, the spectral density. And given that, the question I asked you was, how do you determine the temperature of any star, right? And for that purpose, we noticed that, in addition to that expression, we had an experimental observation. The experimental observation was that the plot of rho versus nu always had a maximum, right? A maximum point, and then it flung down afterwards. The curve just fell off. Okay. Now, then which meant that we had to set the first derivative of rho with respect to nu to be 0 at constant temperature, right? We did that, and we ended up with this expression: e to the power u is equal to 3 by 3 minus u, and we call this as expression u dash. Okay, and where we define u as h nu by kBt, right? Now we continue from here on in this lecture, and in the last lecture, through a series of physical and mathematical arguments coupled together, right? We understood that u lies between 2 and 3, right? We first saw that u has to be positive, so u has to be greater than 0. Yeah, that's something we saw. And after that, we put the value of u to be 3, and we realized that the RHS goes to infinity, but then the LHS had a finite value. Then we substituted u equals 2. We could have as well substituted u equals 4, right? But we had two choices. We chose the u equals 2 one. Okay, you can always try u equals 4 as well, and you'll get some other physical insight. I'll tell you what it is if we have time in the tutorial. Okay, if not, you can take it as a homework. So we chose u equals 2, and when we decided with u equals 2, we realized that the value of the RHS, that is this 3 by 3 minus u, is less than that of the LHS. So from being less when u equals 2, right, it blew up to much more when u equals 3. So therefore, we decided that u has to lie between 2 and 3. Now, when u has to lie between 2 and 3, what do we do? Well, we first check for the various values of u, like 0. What's the problem with u being 0, and then like substituting for u equals 2 and 3, etc. So again, now the choice is to for us to pick up numbers between 2 and 3. How do we do it in a systematic way? To begin with, let's start off with some numbers such as u equals 2.5 between 2 and 3, right? What is exactly in between 2 and 3? 2.5. Okay. Now, let me just I pick up the various values. Okay, right? Let's say I start with u as like 2.5, and I will tell you what happens to the value of LHS, and I will tell you what happens to the value of RHS. Okay, right? So u to the power 2.5, I have tabulated it. Okay, that the LHS is approximately around 12.8. Okay, and the RHS is going to be 3 by 3 minus 2.5, which is going to be 3 divided by 1/2, which is going to be 6. Okay, see, you notice that now again we have a choice. We have a choice of either going to 2.4 or like 2.6. We have a choice. Okay, right? Now, okay, let's take the choice of going to 2.6. We could have of course gone to 2.4 as well. If when u is 2.6, then what happens to the LHS here? This is e to the power 2.6. Okay, and I have written down the value to be 13.5. And the RHS is what? The RHS is going to be 3 times 3 minus 2.6, which is 3 divided by 0.4, right? What is 3 divided by 0.4? So 3 divided by 0.4 is going to be 3 by 4 into 10, right? So that is going to be 7.5. Okay. Now, by looking at these two values, okay, right? Okay, fine. So we've chosen 2.6. Let's go ahead with 2.7 actually. Let's go ahead with 2.7, right? Once we go to 2.7 now, the value of the LHS, I've again noted it, is going to be 14.9. How do I know these values? Well, there are two ways to go about it. The approximate would be to use some approximate value of E as like 2.72 or 2.718, whatever, right? And then try to square, raise it to this power using your scientific calculator, or use your principles of logarithms. Use the principle of logarithms to whatever base, and then you can convert it also to get to these numbers. Okay, it was by the latter approach that I got these numbers. Okay, so when U is 2.7, what is the value of RHS? It is going to be 3 divided by 3 minus 2.7, which is going to be 0.3. That's going to be 10, right? Now, if you notice this, the difference between the LHS and RHS, right, that is actually constantly decreasing. So here this is going to be 6.8. Here this is going to be what? 8.5, 9.1, 9.5. This is 6, and now this is 4.9. So it kind of tells us that we are in the right direction, right? So that's the reason why I'm not worrying about going to 2.4, U equals 2.4. Okay. Instead, what I'm doing is I'm going from U equals 2.5 to 2.6 to then 2.7. Are we all good? Okay. So now let's put U equals 2.8. As I put U equals 2.8, what do I get? E to the power 2.8. E to the power 2.8 happens to be 16.5 approximately. Okay, I've tabulated this. Now what happens to the RHS? Now RHS is 3 divided by 3 minus 2.8, which is going to be 3 divided by 0.2, correct? 3 divided by 0.2. So this number is going to be 3 by 2 into 10. So that is going to be 15. Aha, notice that. The gap between LHS and RHS is further decreasing. It was like 6.8 to 6 to less than 5, which means we are kind of getting here, right? Well, let's put 2.9, right? Let's put 2.9 and e to the power u, right? E to the power u is going to be now roughly e to the power 2.9 is I think around 18.1. 18.1, okay, right? 18.1. And what about like over here, this fellow? So 3 divided by 3 minus 2.9 is 3 divided by 0.1, which is 3 times 10, which is 30. Notice what we have obtained here. There is a change, right? Until U equals 2.8, the LHS was greater than RHS, right? But at this particular point, the RHS is greater than LHS. This implies, okay, right? This implies, right? You get me, right? See, the point of solving an equation is to make the LHS is equal to RHS, right? We have painstakingly obtained that, until some point, the RHS was less than LHS. But suddenly, when the RHS is greater than LHS, we therefore know that the solution is somewhere between 2.8 and 2.9, correct? So we understand from this that U lies between 2.8 and 2.9. Why are we doing all this, numerical calculations? We're doing all this to eventually find out the temperature of a star. Okay, I'll tell you how it is. But look at how the fundamental principles of science, simple, like addition, subtraction, division, right? Exponentiation is going to lead us, hopefully, right? Yeah, to a very profound insight. Please note that point carefully. All right, so U lies between 2.8 and 2.9. Now, at this stage, right? At this stage, I independently verified it, right? And you can also, verify on your own that you can now try between 2.81, 2.89, right? You should go to the next decimal point. Once we saw it was from 2 to 3, we rechecked there, right? And as it turns out, you get the best correlation, right? You will get the best correlation. As a homework, do the math of the number crunching yourself. Okay, so once you do the math, you will find out that your U turns out to be very close to, so close that I can even be done away with the approximate symbol and use exact equality as 2.82, right? So all to solve this equation, right? We had no idea how to solve it, but we once again, what did we do? We did not treat this as an equation in isolation. We understood that there are some physical conditions that this equation has to satisfy. One of which is that, hey, u has to be greater than 0, right? And then by doing some manipulation, we found that u lies between 2 and 3. Then by doing further manipulation, we found that u lies between 2.8 and 2.9. And by asking you to do even further manipulation, I tell you that u is exactly 2.82. Are we good? Right? So what is the moral from this equation? The moral and the message from this equation is that don't give up, just after looking at an equation. You're like, oh, how do I solve it? Look for physical conditions, right? Especially, this is not a math problem to be solved in isolation. It's a problem, an equation which is to be solved in the context of specific physics and chemistry, okay? So always look into the context while solving any equation. The physical conditions are going to be extremely helpful to get various meaningful solutions, okay? On that note, we've now determined our u to be 2.82, okay? I'll now delete all of this because we found out u. Now what is u? U is nothing but h nu divided by kBt. So u is nothing but h nu divided by kBt, right? And this we found to be 2.82, right? We found out h nu by kBt to be 2.82. Now, from this expression, we know h, we know kb, and we know t also, correct? Therefore, we just don't know nu, right? We don't know nu because u is t is what is going to be kept as a constant and nu is what is going to be varied here, right? So we don't know this and this, but we know this, right? So let's substitute the values of h and kb. H is going to be 6.6 into 10 to the power minus 34 in SI units times nu divided by, this is I think 1.38 or 1.3 into 10 to the power minus 23 times nu by t, right? This is what we get here. Are we all good? And this is going to be 2.82. Now what it tells us? What it tells us is that, now notice that nu is one particular point, but what specific point is this nu? It is going to be corresponding to nu max, right? So this is going to be corresponding to nu max. That is, the value, the frequency value wherein, you will be having the maximum rho, right? Wherein d rho by d mu is going to be 0. I'm referring to that as nu max of the frequency. Wait, I'll write it here precisely. Nu max frequency at which rho is max at any given temperature. Because this has to be nu max because we obtained u by setting d rho by d nu equals 0, right? So please notice this, okay? And understand why suddenly I changed my nu to nu max here. All right, okay. Now having understood this, by manipulating this expression right here, okay, by manipulating this expression, I get the idea that my nu, okay, right, my nu is going to be 5.8 into 10 to the power 10 hertz per Kelvin, right? Nu max times temperature. Now this is just the unit, okay, right? Which is in Kelvin. I'm sorry, I'll delete this part, times temperature in Kelvin. I'll also take off the units, why cause so much confusion? Temperature, where this is in hertz and this is in Kelvin. So therefore, this has to be in terms of hertz per Kelvin, which is also the unit of h by kb, right? Okay. Or like, what is hertz? Hertz is nothing but per second, right? So from that you get this. So what have we obtained? What have we obtained? We obtained the relationship between, the nu max and the temperature. Okay, right? So now that we've obtained the nu max and the temperature, right? The nu max can be experimentally obtained, right? So you can perform experiments to actually obtain the new max. Okay, right? Now, once you obtain the new max, of course, you can also convert it into lambda max, correct? Some new max, right? You can always convert it into lambda also. That's trivial because you can always use a nu equals c by lambda, right? And so nu max and therefore this lambda also you can obtain from experiments because c is a constant always. All right? Okay, which means that once I experimentally determine my new max, right? Using this expression, which is called as the Wien's law. It was existing even before Planck's time. However, see, the theoretical curve itself was not applicable to all the frequencies, right? Before Planck. So starting from Planck's equation, Planck made it generalized to all regions of the spectrum, assuming that the blackbody radiation model is true. Okay, right? That's majorly true because when you think about the stars and the sun, right? The atmosphere there is negligible in comparison. So there may be some deviations, but they're all within the error limits, within the significant error limits. Okay. Anyways, so we have this expression. So from this, right, experimentally, after determining nu max, right, using this expression, I'm going to call this expression W in honor of Wien. Okay, right? This is expression W. Using W, you can determine, one can determine the temperature of a star. Isn't it amazing, right? How do you measure the nu max experimentally? You measure, like the frequency of the light coming from the star, right? You measure the frequency of the light coming from the star and you keep plotting it at any given temperature, right? You keep plotting it as a function, as a function of, you keep plotting the rho from the nu, right? You plot it. You know that at any given point, there is going to be a maximum value, right? So this nu max can be obtained experimentally. So once this is obtained experimentally, you use this expression. You use this expression to get your temperature T. Are we good, right? So now therefore, this is how you obtain the temperature of a star itself. I'll say it again, for the sake of clarity. Okay, right? This can be obtained experimentally. How do we obtain it experimentally? Because it is, once you plot rho versus nu, right? For various nus, you understand that there is one particular value of nu, where nu is nu max, which corresponds to maximum rho value, right? So you get this number from experiment, and once you get this number from experiment, right? Now using this relationship, you obtain T. Are we all good, right? So you can obtain T this way. Now, having understood this, okay, right? Having understood that you can obtain T this way, now, see, so the various stars, okay, right? The various stars could have various temperatures, okay, right? So, based on this understanding, I'm just going to write it here itself. I hope there is clarity in the writing. If not, I'll write it again there, okay? We know that when the temperature of a star, okay, when the T star is around 12,000 Kelvin or more, okay, right? 12,000 Kelvin or more, right? Your nu max, right, happens to be in the ultraviolet region, okay, right? And when T star is around approximately 8,000 Kelvin, your nu max, right, is in the blue region of the visible spectrum. How do I say all this? Well, this is because based on this law, right, we can measure the T star, and from the T star, we correlate it with the actual frequency value of nu max. Recall that I have given you, the frequency range for all the regions in the electromagnetic spectrum. Okay, so that's how I tell this. So this corresponds to the blue region, and in fact, if you use a telescope with a color filter, right, you can actually see the color of a star. So a blue star implies that its temperature is roughly around 8,000 Kelvin, and if the T star, is around, like, let's say 4,000 to sometimes even 6000 Kelvin, the nu max happens to be in the red region, right? So you also notice that the nu max happens to be in the red region, right? So I'll delete this part now. I'll just retain the Wien's law expression W alone, and I'll write on this part here. Okay. So the T star is going to be 8000 Kelvin. The nu max is going to be in the blue region. When it's 4000 Kelvin, it's in the red region. You can imagine, right? Therefore, from this, can you predict, the temperature emitted by sun? How do you do this? Well, what's the color of the sun? It's yellow, right? It's yellow. If it's yellow lies between blue and red, right? VIBGYOR. So just based on this discussion, okay, in a very semi-qualitative way, right? Based on the ongoing discussion, we get that sun, right? The temperature emitted, the temperature of the sun as a black body is approximately T is equal to 6000 Kelvin, which is not far off from the actual temperature of the sun, okay, right? So the T is 6000 Kelvin, and that is why it is yellow in color. Are we good, right? So the color of the star actually tells us, what the temperature what the temperature of the star is, okay? And the temperature of the star can be obtained from the black body radiation, right? And look at what we did. The big message from this tutorial is that the last two tutorials, in fact, is that you can start off with a seemingly unrelated expression to obtain unintuitive physical insights, okay, right? An expression which had no relationship. For example, that the Planck's expression that we started with, why should that give us information about the temperature of a star, which could be associated with its color, right? So the bottom line is that two basic science. See, all we used was ideas from basic physics and chemistry, right? We could connect some very far off ideas, such as the temperature of stars, which are like far, far away from us. Okay. So the key is to proceed step by step, because what did we do? For example, here, we started off with the expression. We proceeded step by step, but we first did the calculus, and then we minimized the expression, and then we did some very good algebra, right? It was very, very good algebra, because the equation was not helpful for us. The equation did not want to be solved, okay, right? It was something of the form e to the power u equals sometimes, I don't know, some linear function, right? So that was very difficult. Then we used physical insights, right? And we saw that we narrowed down the range of the solution. Noting that there could only be one solution to the equation, because it's after all, like linear, right, in u. Okay, so there could only be one solution, right? Okay, so we determined that solution to be 2.82, and using that value, we got a very powerful expression using which the temperature of stars could be determined. Are we all good? So on that note, I think this tutorial is formally over, and in the next class, that is in the upcoming class, we shall be starting with the interaction of light with matter. In fact, right after lecture 36, I believe, okay, right? Because for the past 2 hours, we have been having tutorials, okay? So right after lecture 36, my idea was to teach you about the interaction of light with matter. Now that we understood the nature of light and matter, right? But I felt that, it was a long time since we discussed few problems. So it was indeed useful that we clarified several aspects, right? So after equipping ourselves with this problem solving ability, in the next lecture, we shall be continuing our foray into astrochemistry by studying the interaction of light with matter. Thank you so much.